So how do we prove something like this? Well, what you should do is you should go to some scratch paper and write down two odd integers, but you can't just write like 7 and 9. Well, you could, and you add 7 and 9 and you get 16, right? So you feel good about it. And then you know, if you sit there and add two odd integers for a while, you're gonna say, okay, it seems like this is true. But then what you need to do is you need to sort of do some scratch work and take two generic odd integers and add them together and see what your generic integer is. Is it even or odd? So here is what we mean by a sort of a proof. So what I'm going to do is let n equal 2k plus 1 and m equal 2j plus 1 be odd integers. Now, when I write this now by context tells the audience, whoever's reading it, if I'm telling you n and m are odd, that means k and j by definition have to be integers. That's the definition. Right? The definition of an odd integer is 2 times integer plus 1. So if I have two different odd integers, I'm going to say one is 2 times k and the other is 2 times j. Okay. So now we add. Then what is n? What is their sum? Their sum is n plus m, which is equal to what? If we go to the next page, this is going to be 2k plus 1 plus 2j plus 1. Now, I don't need these parentheses, but I'm doing that just so you understand that this is the number n and this is the number m. And so when I combine like terms, I'm left with, when I combine like terms, I'm left with 2 times the quantity k plus j plus 2. So let's call or let's not say call. Let's write it a little better. So let's set L equal to k plus j. Since k and j are integers, L is also an integer. And then since n plus m equals 2L plus 2, which can also be written as 2 times L plus 1, we conclude n plus m is even. And that is the proof. We showed that n plus m is 2 times an integer. Does anybody have a question about this? So problems 1 through 4 are very much of this flavor. Now, there are other ways to make this argument that are also correct. And perhaps they're more concise than this, or perhaps they're more clear than the way I've written it. If you want to see more, go to the internet and type into the Google search, prove that the sum of two odd integers is even. See what they write. See if you like their version better. Remember, one of the goals of this class is to not only make you or expose you to the idea of proof, it's for you to become better. Now, the fact of the matter is no one is expecting you to even be good at it yet. That is part of this course. So do not get frustrated when you're confused. That's natural. You're going to be confused. Everybody is. When we transition from what we call procedural math to real math, people freak out. That's okay. That's part of the fun. So I was worried years ago. You'll be worried, but you'll be able to suffer, or you'll be able to suffer. It's a bad word. You'll be able to make it through. Oh, excuse me. Does anybody want to say anything about this problem before we move further? All right. Okay, so very good. Let's look at number 5 now, because this is important. Many statements and theorems in mathematics come in the form of what we say an if and only if statement. And this is that biconditional we talked about. So we want to prove that if n be, let's suppose that n is a positive integer. We want to prove that n is even if and only if 7n plus 4 is even. So let's just kind of verify this for a number n. So here's what you should be thinking about. So before writing up a proof, or as I'd like to say, an official proof, let's play around. Or let's sketch some ideas. And brainstorm. So oftentimes a proof is just not direct. It's not just going to come to you right away with, now some of them like 1, 2, 3, and 4, if you've done a few of those types of proofs, you're going to say, okay, great, I see kind of what's happening with these. But those are more like the exception, not the rule. Most proofs require lots of thought and effort and trial and error before you arrive at the logical reasoning. Is that clear? This is not algebra homework where if you've done 3 examples, the next 15 are the same damn thing. This ain't how this works, right? This isn't like mimicking procedural. This ain't calculus where you learn a chain rule and every problem you differentiate requires the same procedure. This is not procedural. This is a lot different. So you have to get out of that way of thinking. So first off, let's note, first couple things I'd like to do is let's mentally check. Or what I like to say, gauge its validity. So I'm going to choose a positive integer. So let's check a few n's. So let's say n equals, I don't know, what's a good even integer? How about 8? And if n is 8, what is 7 times n plus 4. Well, that is 56 plus 4, which is, of course, 60, which is even. So it checks out when n is 8. Do you understand what I'm saying here? What I'm just doing is getting a feel for what this thing is asking me to verify. This statement says that if I have a number n, it's even, then if I multiply it by 7 and add 4, it should also be even. That's what it's telling me. So we verified that it's true when n is 8. But that's not a proof. That's just sort of like, hey, it's true in one scenario. So how about if n is 20? Well, what is 7n plus 4? Well, in that case, that would be 144 is even, and so it checks. Now, once we check a few of these, and maybe, you say, well, you didn't ask us to check them, but I understand that. When it says to prove something, though, it's not always obvious how to start. So one of the first things you can do is look at this statement or the theorem that you're trying to prove and study it in special cases. Here, I investigated it in 2 special cases. Special case 1, the number was 8. Special case 2, the number I chose was even, and it was 20. Is that clear? So I looked at it in 2 special cases. And now notice why it's working, though. The reason it's working is because I'm taking 7 and multiplying it by an even number. And that even number has a factor of 2 in it. And so then when I add 4, there's also a factor of 2 there. So what I'm seeing is I have a factor of 2 in both places. So I might not even have needed to do this little self-check in 2 scenarios. But even though I did, I start to get an idea of how I can go about proving this. Now, the fact of the matter is, though, if you look at this statement of this theorem, it has this very, very important thing that says, if and only if. So those words mean that there's actually 2 implications going on. That means we assume n is even, and that implies that 7n plus 4 is even. And then that the opposite is true. I shouldn't say opposite, the converse is that if 7n plus 4 is even, then n must be even. So we have to prove 2 directions here. Now, I wrote that down because I know it's not necessarily clear because you guys are just babies learning logic. But I wrote after problem 5 on the homework, remark, to prove P if and only if Q, you have to do 2 things. You have to prove P implies Q, and then you have to prove that Q implies P. Now, what happens often in theorems of this is that one direction is really easy. And then what happens is typically, not all the time, but typically the other direction requires some work, some ingenuity, some new ideas. Right? So we think, and here's kind of where I'm at. So it seems proving n equals 2k, that is, I mean, this is sort of math speak for this is n equals even. So it seems proving this implies 7n plus 4 is even. Might be straightforward. So perhaps we should see if we can knock it straight out, which we will likely be able to do. So let's just see if we can do that. let's just see if it works. Can we sketch it out? So if n equals 2k, 7n plus 4 will equal 7 times 2k plus 4, which will equal, if I rewrite this, 2 times 7k plus 2. This guy right here is an integer. And so since that's an integer, let's give it a name. Let's call it J. So what did we just prove here? What we just showed, and we're going to write this up in a polished manner in a little bit, is we just showed. So we just proved that n equals 2k implies 7n plus 4 equals 2j. Hence, 7n plus 4 is even. So this direction required nothing more than taking n and assuming it had a certain property. That is, we assumed n was 2 times an integer, 2k. And then we plugged that into 7n plus 4, and we just did a little bit of algebra. We factored out of 2, and we rewrote it. And we've rewritten it as 2 times something. In particular, we wrote it as 2 times j. So what we've done is we've proved one direction of this theorem. Now, we're not done because we have another direction to prove. But we at least got half of it. Does anybody have a question, a comment, a concern? Does anybody want to point something out? Anybody? No, we good? So you might wonder then, well, if I prove the converse, if I prove Q implies P, is that going to be just as easy? And it turns out it might not be. So let's see that. And I guess it's not going to be. The same strategy we proved to go one direction. And by the way, if you keep hearing me say P and Q and you're like, what is he talking about? Well, remember, we're thinking of these things as a proposition implies another proposition. So P is the proposition n is even. Q would be the proposition 7n plus 4 is even. Or statements, I guess, because they're not propositions, because we can't say they're true or false unless we say they're going to be true. Okay, so here, this is good. We're happy here. Okay, so now we have to get into some more sort of brainstorming again. So the question then becomes, how then do we prove, let's say 7n plus 4 is even. Now, I don't know anything about n other than it's a positive integer now. I'm not assuming it's even. I'm assuming 7n plus 4 is even. So how do we prove that this implies, well, let me write it more carefully. How do we prove this even implies n even? So we might try to do the same reasoning. We might try to assume that 7n plus 4 is 2 times something, and then reason that n is 2 times something. So let's try that. So we might try a direct proof. by saying, or by assuming 7n plus 4 equals 2 times, I got to use some other letter. I'll use m. So m is an integer, and if I assume that 7n plus 4 is even, that means that I can write it as 2 times m. Pick an even number. What's your favorite even number? You say, I like 10. I can write it as 2 times 5. Pick any even number. The definition of being even means you can write it as 2 times something. Okay, so let's see what happens if we do this. So the question then becomes, can we conclude n equals 2 times, I don't know, what letter haven't I used yet? Let's say n equals 2 times I for some I. Can we do that? Well, let's try. So let's say, okay, if I have 7n plus 4 equals 2m, I might think that this is implying that 7n equals 2m minus 4, and that implies that n equals 2m minus 4 over 7. Here's the issue with this. You might even get cute, and you might say, well, O'Grady, we're done. Because you might say, okay, this is equal to, I'll factor out a 2. You'll say 2 times m minus 2 over 7. The only issue is with this particular line of reasoning is the following. How do we know this is an integer? I mean, if I just take some number m, if I take 5 minus 2 over 7 ain't an integer. Do you understand the dilemma we're in here? So using this direct algebraic reasoning like we've done today and last week isn't helping us here. How do we conclude that m is in fact, or excuse me, m minus 2 over 7 is in fact an integer? It's not at all obvious. I mean, again, I just gave you, pick another one. Pick m equals 6. 6 minus 2 is 4. 4 over 7 ain't an integer. Now, you might think that that means that the statement's false because this reasoning, but maybe we're just not thinking about what m has to be. So first off, if we assumed n is a positive integer, then the left hand, 7n plus 4, the smallest it will ever be is 11, right? Because if n, the smallest n can ever be is 1. So if n is 1, then you're getting at 11. What happens when n is 2? Well, when n is 2, you get 2 times 7, which is 14 plus 4. Right? So is there some argument that we can make that would actually make it easy to verify or conclude that m minus 2 over 7 is an integer? And maybe there is, but instead of looking at it, let's realize what we could do here. So let's think, and this is what we call good quality analytic thinking. We realized it was really easy to show if n had a property that 7n plus 4 had a property. So instead of trying to prove the reverse direct, why don't we prove the reverse using the contrapositive, because then that proof will be nearly identical to the one we just did. So again, let's emphasize that this was a dead end. So let's write that down. So the direct attempt was not logically sound. So perhaps we try a proof by contrapositive. So that means proving that 7n plus 4 even implies n even. That is logically equivalent to, or as we say, logically the same as, n odd implies 7n plus 4 odd, which we know to be an easier thing to prove. At least experience tells us that. So let me reiterate this for everybody here, because this is a very important sort of fact. Maybe not fact, maybe a better way of saying it is an important concept, idea. And that is, oftentimes when a proof is of this, or excuse me, a theorem is stated in this manner, in one direction is easy, it is oftentimes that the other direction is hard. However, it's only hard if you try to prove it directly. If you use a contrapositive, that is, not Q implies not P, then it's often a little easier to prove. And in this case, what's nice is when you think about what happened, if we only assume something about n, we can usually use algebra to deduce something about an expression involving n. But the other way was more difficult. If we assume something about an expression in n, it was much more difficult to deduce something about n itself. So let's try it this way. So assume this is the case. So n odd, by definition, the definition here implies that n equals 2k plus 1 for some k. So don't forget, I'm being this is kind of like my scratch paper, all this stuff. This is not a polished proof. This is all my brainstorming, my playing around, my sketching, my what I call scratch work. This is all the stuff that you never really see when you see a theorem and a proof in a book. You see the polished result. You very rarely see all the work that was put into getting the polished result. We'll do that at the end, but let's make sure this works first. So if I assume that n equals 2k plus 1 for some k, that's the definition of being odd, then 7n plus 4 equals 7 times 2k plus 1 plus 4. And all I want to note is that I can write this in a special way. I can write this as 14k plus 11. Now you're going to say, what good is that? Well, another way of writing 14k plus 11 is to recognize you can write 11 as 10 plus 1. So this becomes 2 times 7k plus 5 plus 1. Now, of course, you're going to say, huh? How did I ever think of that? You ever pay attention on the internet when all these jabroni parents are mad because their kids have math homework and the parents can't help them, and then they bitch and moan and they say, the new math is terrible, this is stupid, let's go to the old way. And the thing is what the new math is trying to help teach you is how to reason in these kinds of ways. Yes, I know that 7 plus 4 is 11, but sometimes we don't want to think of 11 as 11. Sometimes it better suits us to think of 11 as 10 plus 1. And if I think of 11 as 10 plus 1, I can write 14k plus 11 as this, which you're going to say is silly. Why would I do that? Well, why would I do that? Because now this is of the form, call this j. Now I have 2j plus 1, which means 7n plus 4 is in fact odd. And we've logically proved it. There's no ifs, ands, or buts about it. And we're real happy with ourselves. Of course, you're like, no, I'm confused. This is crazy. That's what you're thinking. I'm never going to be smart. That ain't true either. Well, you should have seen me back in like 2000 when they were trying to teach me this. You weren't even born yet, but it was a wild time for me. I was like, what in the world are they asking me to learn? This ain't math. Does anybody have a question about this? Tell you what, it is thirsty. What is the fancy line? Parched. Okay, so what we've done is we've gotten to a point where we can now put all this in a nice, pretty bow. We've sort of, a good way to think about this is we took a box of a puzzle and we threw all the pieces and spread them out on the table. And we put all these ones here in this pile and these ones here in this pile. And we started doing all this deductive reasoning. These must be edges. These must be centerpieces. These have red. These have some woman's eyes, whatever. This is a mountaintop, whatever puzzle we're building. And eventually we finally put the thing all together. So that's what we have to do now. We have to make it look like a nice, pretty piece of art, and it will scare all the other people who didn't see all the work that went into it. So let me repeat it, that we spent now, that's 1 page, 2 pages, 3 pages, 4 pages really already of just figuring out what to do. So it's time for a polished proof. And that's what we're going to do now. Unless someone wants to say something like, hey, how was everybody's weekend? So let's sort of restate the problem. So it's time to write up our polished proof. So let's remember what the statement of the problem was. It said, let n be a positive integer. And by the way, you might actually say, well, where did we use the fact that n was positive? That's a good subtlety. We never used that assumption anywhere, did we? We sort of did without saying it. That's a good question. Where did we use that assumption that it was positive? Did we need it? That's a good question. Was that an assumption that was unnecessary? I'll let you think about that. Anyhow, let n be a positive integer. Then n is even if and only if 7n plus 4 is even. So I'm going to break this proof into 2 pieces. Here's how you might want to write it up. So So let's delete this. So we're going to start this off as assuming well, okay. Maybe we'll be a little more careful. Let's not go too fast. So when you have a statement of this type, an if and only if, as I said, you have to do two things usually. Not all the time, but and there might be a creative way to put it all into one, but typically we have to do two things. P implies Q, Q implies P. So first, assume that n equals 2k, where k is a positive integer. Now, why am I saying that? Well, that is the definition of n being a positive integer that is even. So what we will do is we will show 7n plus 4 is even. So notice how I've written this. I've written this as a P implies Q. I've written it as P is the statement n is even, and then I'm saying we will show that 7n plus 4 is even. So that's the if P, then Q. So how do we go about doing this? We already saw this direction is a plug and rewrite. So note that 7n plus 4 is 7 times 2k plus 4. Which can be written as 2 times 7k plus 2. So what does this line tell us? Well, since k is an integer, seven k plus 2 is an integer. Thus, 7n plus 4 is even. It satisfies the definition. 7n plus 4 is 2 times an integer. So you may have a question about this. So that's the one direction. So let's make a note of that. It remains to prove 7n plus 4 even implies n is even. And so we found out a good way to do this, and that is we'll use the contrapositive. So to do this, we use the contrapositive. So the contrapositive means we assume n is odd, so that n equals 2k plus 1 for some k. Or being very specific, let's say for some integer k. So that is the definition of being odd. Okay. We must show 7n plus 4 is odd. And then we can reason as follows. Indeed, what is 7n plus 4? 7n plus 4 is 7 times 2k plus 1 plus 4, which, if I creatively write this, is 14k plus. Remember, I don't want to write this as 11. I want to write this as 10 plus 1. And when I do it this way, I get 2 times 7k plus 5, all plus 1. And then we can reason, since k is an integer, seven k plus 5 is an integer. Therefore, 7n plus 4 is odd. And so the proof is complete. We often put this little box here. So there's an awful lot going on here. And it would be in your best interest as amateurs and beginners to really think about why we did what we did in this particular problem. Does anybody have any questions? Comments before we go and do some more? So let me emphasize this fact again, because I think it's extremely important. We spent a lot of time sketching and working this out. Now, some of you don't need that much time. Some of you are going to get this quicker. I don't want to say quickly, but quicker than others. That's okay. Some of you are going to ask yourself, do I really need to write all that out? Can I skip some stuff? And that's sometimes you'll be able to, I don't want to say skip stuff, but omit certain things in context, if you will. But I caution you at this point as amateurs that you should be writing out everything. I mean, the purpose of this is for you to learn sort of how to go about this. And how do you go about it without sort of making cheating, so to speak, or reasoning incorrectly. The other question I would point out is where, if anywhere, did we need the assumption that the integer was positive? Does it work for odd ones? Is there something in our proof that we weren't sort of doing properly? Anybody have a comment or a question about that? Going once, going twice. Does anybody not see what I mean by that? Where did we use the assumption that n was where did we use it that it had to be positive is a better way of saying it? No, we stated that, but where did we use that fact? Did we use that fact anywhere? Did any of the algebra we used, for example, rely on the fact that the number we are dealing with could not be negative? It's a good question. That could be a good extra credit question. Yeah, so your points are well taken, Jared. It's a good thing to ask, and it's okay. Sometimes we make assumptions that are unnecessary. So what I'm saying is, from what we did, would it be wrong to state the theorem as just if n is even, then 7n, if and only if 7n plus 4 is even? Was there anything about our algebra that would preclude that argument from being sound in the if we started with like -2? So for example, what -2? -2 times 7 is -14, right? -14 plus 4 is -10. So by definition, that's an even number. So you might convince yourself that it's true for negatives too, right? So you might ask, why is it stated that way? These are good questions to ask. That's how we learn. Why? What's wrong with that? All right. So anyhow, let's move on. I'll let you ponder that. Problem 6 is very similar to what we just did. Here's a good problem. How can you prove that there's no integer that satisfies this equation? So there's a very, you guys have spent a ton of time studying equations. That's mostly what your days in school math were with algebra. But it turns out in many instances, we're not worried about real number solutions. We're more curious about integer solutions. And these things date back to as long as we have written history. We'll study them a little more probably in this semester. They're called Diophantine equations. It's an equation where we're interested in only if there's integers that satisfy it. So what some of you would do with number 7 is you might incorrectly reason is like, let's factor out an n squared and say, you guys create your own rules all the time that I'm always baffled by. I would have done the same thing as a student. But how can we reason how can we reason that? Well, let's look at positive. Let's look at sometimes we get insight by just plugging and chugging. So let's look at this problem. So number 7. Can n squared plus n cubed equals 100 have a positive integer solution. How can we reason this logically? So this is going to show us a different type of reasoning than what we've done before. What we did earlier is we sort of assumed something. Right? Now we're asking a different question. We're sort of saying prove that no integer will work. Now guess what? How many integers are there? Start counting, you ain't going to survive it to the end, right? You can't check them all. But sometimes we can reason that there's no reason to check them all. For example, pick a number like 10. What is 10 squared? What's 10 squared? 100, right? Well, then 10 clearly couldn't work. So here's how you might reason. Since 10 squared is equal to 100, 10 can't work. In fact, n greater than 10 won't work. If 10 can't work, look, hold on, let's make sure we understand why 10 can't work. You realize it's impossible for 100 plus a number that's positive to equal 100. We understand that, right? So if you try to place 10 in there, it can't work. Similarly, what about a cubed? Well, I don't know, what's something like 5 cubed? Well, 5 cubes bigger than 100, right? So similarly, 5 cubed is greater than 100. So n greater than 5 can't work. Well, okay, so Jared asked, is this basically searching for least upper bound? No, I think you're in the right world of what we're doing here, but you're using incorrect terminology. What we're doing is we're eliminating. What we're recognizing there's only so many choices that could possibly work. So this means we'd only have to check, or we'd only have to check n equals 1, 2, 3, and 4. Turns out none of them are solutions. That's the way to think about this. So a better way of maybe phrasing what you were saying, Jared, is we're looking for what are the possible, who even qualifies to be a candidate for a solution. We were able to reason out all but 4 choices. So one way of saying what you're saying is if you're going to be a solution, the largest you could be is 4. Yeah, defining constraints is a good way of thinking about it, yes. Does anybody have a question about this? So why is this a good example? Well, a very common error amongst amateurs, and even those who aren't amateurs, is you guys often think you can prove something by showing it's true for a couple scenarios. Right? You'll say, oh, it's true because it was true for this, this, and this, but that's not always valid. Oftentimes, that's incorrect reasoning. If, you know, we have these quantifiers, we have these things like there exist or for all. If you want to show something's true for all, you have to logically show it's true for all. So what we just did is we showed that this equation has no solution for all positive integers. But the way we are able to do that is we reasoned that it would be impossible for any number larger than 5 to work. So all we had to do then was check the first 4. And if you plug the first 4 integers in that are positive, neither of them are going to work. Verify for yourself. You plug in 1, last I checked 2 ain't 100. Plug in 2, last I checked 12 ain't 100. Plug in 3, last I checked, what, 27 and 9, so what, 36 ain't equal to 100, right? So those guys can't work. Now, normally you'd have to check 5, 6, 7, 8, 9, 10 forever and ever and ever. Problem is we don't have to here. Actually, I said the problem is the good news is we don't have to, and the reason we don't have to is because once we get to 5, 5 cubed is already bigger than 100, which means 25 plus 5 cubed is, they don't fit a constraint, is the word you used. You know, they're not even in the realm of being a solution. Does anybody have a question about that? Are there any negative integer solutions? Actually, turns out there's not, but that's a little more difficult to reason. That's why we didn't ask you to do it. Okay, so fair. That's a fun sort of problem. Does anybody have a question about this? All right, so let's look at perhaps what we're going to do. Actually, I just had an idea. If I go back to your homework, I have hereby. Now, this does not mean don't do it. I am going back to your homework, and I am saying you should. We will turn it in Monday now. Well, you could turn it in whenever the heck you want. But so if you already submitted the homework, feel free to resubmit. I won't be mad. We will make it due Monday night at midnight because I'd like to talk about some of these problems at the end in more depth than we've done so far, and we're out of time. So does that make sense? Hopefully you guys all know what an irrational and an irrational number are. And what I'll sort of foreshadow to, and I hope you study this, is let's go. Hopefully you guys can do number 9. Number 10 is one of the most famous proofs there ever were, and also perhaps the oldest proof we have out there. So prove square root of 2 is irrational. And so we'll talk about this in depth on Monday, but what you should do is the idea is to assume it is rational and exhibit a contradiction. So this is a famous sort of method of proof. And there are solutions to this, or proofs, I should say. One of the first was given by Euclid. I'm sure there's others in different cultures, perhaps. But it's one of the original proofs that we have, particularly of using what we call proof proof by contradiction. So I guess maybe I shouldn't say it dates back. Well, we can do this culturally sound. So Euclid, if you don't know who he is, Google him. And since I was educated with the Western textbooks, I don't know for sure that someone else doesn't get credit for this as well. See, I'm culturally sensitive, you guys. You guys don't even know what you're getting with me. So we will leave the door open that perhaps others have also done this, not just what they teach in Western schools, as they say, Western. Like Nas will remind you, algebra was discovered in Africa and the Middle East, which is true. Not in London. All right, very good. So we'll talk about this in detail. This is the thing, but I want you guys to go ahead and look at it. So we'll do this on Monday. Hopefully you guys will give it your earnest attempt. And then also, and by the way, I'm skipping 9 and 11, but you guys need to think about them as well. And then how do you handle something like 12 and 13? So hopefully you guys will give those sort of an honest attempt. Any questions, comments? All right, well, listen, I will end this party. Thank you very much for joining us. And I will, if you have questions, email me. Otherwise, I will see most of you Monday, some of you tomorrow and Friday. Take care, guys. Thank you.